Hey, good morning all. Good morning. I hope you guys did not spend all of last night celebrating the Red Sox victory, but there's one more tonight. Okay. Let's see. I trust the quiz went okay. What I'll do today is take off from where we left off on Tuesday, and continue our discussion of the large signal and small signal analysis of our amplifier. So today, the focus will be on small signal analysis. So let me start by reviewing some of the material. And as you know, our MOSFET amplifier looks like this. One of the things you'll notice in circuits, as I have been mentioning all along in this course, is that certain kinds of patterns keep repeating time and time again. Okay? And this is one such pattern. A three-terminal device like the MOSFET with an input and the drain-to-source port connected to RL and VS in series in the following manner. This is a very common pattern. There are several other common patterns. The voltage divider is a common pattern. We keep running into that again and again and again. The Thevenin form, a voltage source in series with a resistor, is another very common form. The Norton equivalent form, which is a current source in parallel with a resistor, is also very common. And it behooves all of us to be very familiar with the analyses of these things. Voltage dividers in particular are just so common that you need to be able to look at it and boom, be able to write down the expression for voltage dividers. I would also encourage you to go and look at current dividers. When you have two resistors in parallel and if you have some current flowing into the resistors, to find out the current in one branch versus the other very quickly. Okay, the expression is very analogous to the voltage divider expression. And some of these very common patterns are highlighted in the summary pages in the course notes. So it's good to keep track of those and be extremely familiar with those patterns to the point where you see it, you should be able to jump up and shout out the answer just by looking at it without having to do any math. Okay. So here was an amplifier. And then we noticed that when the MOSFET was in saturation, it behaved like a current source. And this circuit would give us amplification while the MOSFET was in saturation. So we agreed to adhere to the saturation discipline, which simply said that I was going to use my circuit in a way that the MOSFET would always remain in saturation in building things like amplifiers and so on. Okay? And by doing that, throughout the analysis, I could make the assumption that the MOSFET was in saturation. Okay? I didn't have to go through both. Analysis became easier. I didn't have to figure out, now, what region is the MOSFET in? Well, because of my discipline, it's always going to be in saturation. But in turn, what we had to do was conduct a large signal analysis. Again, in follow-on courses, you will be given circuits like this. In fact, this very circuit with a very high likelihood, and you'll be looking at more complicated models of the MOSFET. Or you may be given a MOSFET like this, and let's say in that course, the designers do not adhere to the saturation discipline, in which case you have to first figure out, is my MOSFET in its triode region or in the saturation region? And depending on the region it is in, you have to apply different equations. Okay, so it's one step more complicated than in 002. In 002, we simplified our lives. by following a discipline. Okay, and let me tell you that following a discipline is quite okay. Okay, when it simplifies our lives and we can do good things with it, it's quite okay to do that. Okay, we're not wimps or anything like that. It's, it's quite okay to have a discipline and agree that we're going to play in this region of the playground and build circuits in that manner. So by doing so, we could assume the MOSFET was in saturation all the time. And our analysis simply used a current source model. By the same token, what becomes important is to figure out what are the boundaries of valid operation of the MOSFET in saturation. Okay, so to do that, we conducted a large signal analysis, and it had two components to it. One, of course, was to figure out output, the output versus input response. And what this usually does is that it does an analysis, a nonlinear analysis of this circuit. If it's a linear circuit, it's a linear analysis, and figures out what the values of the various voltages and currents are in the circuit as a function of the applied inputs and chosen parameters. And the second step, we said, was to figure out valid operating ranges. For input and corresponding ranges for the other dependent parameters, such as V0. Okay, you could also find out the corresponding operating range for the current IDS, and so on. Okay, so by doing this, you could first analyze the circuit, find out the bias parameters, find out the values of VI and V0 and so on, and then you could say, all right, provided as long as VI stays within these bounds, my assumption that this is in saturation will hold, and everything will be fine. Okay, so the reading for this is chapter 8, and today we'll take the next step and revisit small signal analysis. So in the demo that I showed you at the end of last lecture, I showed you an input triangular wave, and that input triangular wave gave rise to an output. And we noticed that we did have amplification. Okay, I had a small input, I had a much bigger output. I did have amplification when the MOSFET was in saturation, but it was highly nonlinear. Okay, the input was a triangular wave, and the output was some funny, it kind of looked like a sinusoid whose tips, whose extremities had been whacked down and kind of flattened, and its upward going peak had been shrunk. So it was kind of a weird nonlinear behavior. I'll show that to you again later on. And so the behavior, it amplified, but it was nonlinear. Okay? And remember our goal of 2 weeks ago, we set out to build a linear amplifier. Okay? So today we'll walk down that path and talk about building a linear amplifier. So to very quickly revisit the input versus output characteristic, VI versus V0. This is VT, and this is VS. This is what things look like. We also, to quickly review the valid ranges, until some point here, the amplifier was in saturation, the MOSFET was in saturation, and somewhere here I had VI, rather VO being equal to VI minus a threshold drop. At that point, the MOSFET went into its triode region, and I no longer was following the saturation discipline. So therefore, this is my valid region of operation. We also know that the output was given by Vs minus K, Vi minus Vt whole squared. Okay, again, assuming the MOSFET is in saturation. Okay, it's very important to keep stating this, okay, because this is true only when the MOSFET is in saturation, when I'm following the discipline. So notice that this is a nonlinear relationship. So VO depends on some funny square law dependence on VI. So the key here is how do we go about building our amplifier? So so take a look at this point here. So at this point here, let's have a VI input. Corresponding output is V naught. Focus at this point, okay? And left to itself, this is a nonlinear curve. Okay, and remember the trick that we used in our nonlinear, the expo dweeb example. We used the Zen method. Remember the Zen method? We said, hey, look, this is nonlinear, but if you can focus your mind, if you can focus on this little piece of the curve here, okay, this looks more or less linear. Okay, if I look at a small itty-bitty portion of the curve, and do the Zen thing, okay, and kind of, zoom in on here, this looks more or less linear. Okay, this means that if I could work with very small signals and apply the signal in a way that I also had a DC offset of some sort, then I would be in a region of the curve. I would be delineating a small region of the curve, and which would be more or less linear. Okay, this was a small signal trick. And what we'll do here is simply revisit the small signal model. Okay, most of what I'm going to do from here on will be more or less a repeat of what you saw for the light emitting expo dweeb. Okay, just that here I have a 3-terminal device. Okay, a little bit more complication. The equation is different. Okay, I don't have to resort to a Taylor series expansion. I'll just do a complete expansion of this expression and develop the small signal values for you. Okay, so recall the small signal model. Okay, had the following steps. The first step was operate at some bias point, VI, V naught, and of course some corresponding point IDS. This is page 3. And then superimpose a small signal VI on top of the big fat bias. Remember the boost? So VI is the boost. Boom. And above VI, I have a small signal VI that I apply. And our claim is that response of the amplifier to VI is okay. So the key trick with this is that for my small signal model here, this is page 3 here, page 2. So the key trick here is that with the small signal model, I operate my amplifier at some operating point, V naught VI. Superimpose a small signal VI on top of small VI on top of big VI. And then I claim that the response to VI is approximately linear. Okay? And let me just embellish that curve a little bit more. Notice that in this situation, this was my VI, which is my bias voltage. This is V naught, which is the output bias. And of course, not shown on this graph is the output operating current, which is IDS. Okay? So one nice way of thinking about this is to redraw this and think that your coordinate axes have kind of shifted in the following manner. So this is VI. This is also on your page 3. This is VT. Remember, this was your operating point, V naught and VI. And notice that we were operating in this small regime of our transfer curve here. And in effect, what we're saying is that I'm going to apply small variations about VI and call those variations delta VI or small VI. And the resulting variations are going to look like delta V naught, also referred to as small v, small o. Okay, so I have small variations here, and they give rise to a corresponding small variations there. So one way to view this, okay, is as if we are working with a new coordinate system. Okay, another way to view this is that, so the V capital I and V capital O correspond to my VI and VO as the total voltages in my circuit. But at this bias point, I can think of another coordinate system here with small VI and small VO out there. And for small changes to VI, I can figure out the corresponding small changes to VO. Just that all the analysis I performed here is going to be linear, and I'll show you, and I'll prove it to you in a couple of different ways in the next few seconds. Okay? So when I'm doing small signal analysis, I'm operating here, okay, in this regime at some bias point. So you've also seen this before. How do I get a bias? So this is my amplifier RL and VS. This is page 4. V0. Okay, the way I get a bias is I apply some DC voltage VI and superimpose on top of that my small signal, small VI. Okay, this is my DC bias that has boosted up the signal to an interesting value. Okay, and because of that, what I can get is by varying VI as a small signal with a very small amplitude, I'm going to get a linear response here, and I can draw that for you as well. Okay, so this is my bias point here, and if I vary my signal like so, then my output should look like this. Okay, so this is point VI, this is point VO, okay, and this is my small signal VI, and this is my small signal VO, and this is capital VO. Okay, so this small thing here is VI. I'd like to show you a little demo. I'll start with the same demo I showed you the last time. I showed you the amplifier. In the demo, I'm going to apply a triangular wave. And initially, I start with a large signal. Okay, and you will see that the output looks really corny. It's going to look, something like this. Okay, that's the large signal response. And then I'll begin playing with the input, making it smaller, and you can see how it looks yourselves. There you go. So this is where I stopped the last time. And in the last lecture, I applied this input. Time is going to the right. And the purple curve in the background is the output. Okay, it looks much more like a sinusoid with some flattening of its tips. Nothing like an interesting triangular wave. So what I'll do next is that let me make sure I have enough of a boost here, enough of a DC voltage so that I'm operating at some point here. I believe I already have that. So notice that I can shift up the triangular wave input, or I can shift it down. So let me bias it here. So I've chosen a VI that's about, I forget how many volts per division it is, but I've chosen some VI here, and I've biased it such that this is the input. Now what I'll do, you get a nonlinear response. It's amplified. It's much bigger. So what I'll do next is make VI that I apply smaller and smaller. Okay, I've already done the boosting. Boom. Okay, boom. That's a boost. Okay, so I've boosted up your VI already. Next is I'm going to shrink it, and hopefully you will see that if all that I'm saying is truthful here, you will see a triangular response. Well, let's go try it out. So watch the yellow. I'm going to shrink the yellow, make it smaller and smaller. There you go. It's great when nature works like you expect it to. So I've never seen a triangular wave look so pretty in my life. It's awesome. So, look at this. Here's a tiny triangular wave. And the output is also a triangular wave. It's much more linear. Yes, question? What's that? The question is that, your output here is only as big as the input used to be before. Now, that's a good question. What I've done here is I'm showing you a laboratory experiment, all right? And let's assume that this input is the input I'm getting from some sensor in the field. Okay, assume that this is my input. Okay, not what I had before. Okay, assume that this is my input to begin with, and this is the amplified output. What I can also do is I can also change the bias, and we'll see this at the end of the lecture, in the last 10 minutes of lecture. How do you select a bias point? Okay, by changing your bias point, you can change the properties of your amplifier. To give you a preview of upcoming attractions, all right, let me ask you. So what do you think should happen if I change the bias point? I haven't shown you the math yet, so intuitively, what do you think should happen? If I increase the bias, what do you think is going to happen? Yes?
Higher bias will be more amplification.
Good insight. Higher bias will be more amplification. Okay, let's see if our friend is correct. We should change the to 3 here. Okay, here. All right. So let me set a higher bias. Not necessarily, I guess. You're actually right, by the way. Okay, I'm playing a trick on everybody here. Yeah, let's do that. Okay, so as I change my input bias, notice that under certain conditions, my output becomes smaller, okay, and gets more distorted. Okay, under other conditions, what's going to happen to my output is that it's becoming smaller and it's going to get distorted again. Okay, so there are a bunch of funny effects happening that reflect on the bias point. But for an appropriate choice of bias point, as I increase the bias, the amplification should indeed increase, and I'll show you that in a few minutes. Yes, but it's a complicated relationship. Yes.
So how do you actually get, like, if you want to really amplify it so that's huge, how do you do that?
This is finally getting fun. Okay, so here's the question. So, yeah, Professor Agarwal, we love your song and dance, but if you really want to get a high signal at the output and you want to amplify a big input signal, how do you do it, right? So the question is, let's say I have a input that's this big here. If it's this big, I've shown you how I can get things that's this big. But what if my input was this big? How do I get an output that's this big? Well, I'll use one of those learn by questioning methods and have you tell me the answer. So someone tell me the answer. How do I do that? Yes? Use another amplifier. So the answer is, okay, so I use one amplifier to go from here to here. Okay, and the suggestion is use another amplifier to go from here to here. And in fact, I believe that you may have a problem in your problem set where you will do that. Okay, and so how do you? You have only yourselves to blame. All right. So how do you make this work? What you have to do is this VI has to be much smaller than the bias point VI on this one. I have to build a different amplifier, choose a different set of parameters such that VI prime, which is the VI for this guy, is much less than V capital I prime for this guy. It's a design question. Okay, you need to design it in a way that the signals of interest need to be much smaller than the bias voltage of this amplifier. So you may have to use much higher supply voltages. My amplifier, I believe, has a 4-volt supply or 5-volt supply. You may have to use an amplifier with a much bigger supply, different values of RL and so on. Okay? And I know that the course notes also has some exercises and problem sets that discuss that in more detail. Yes?
Why do you need the middle step with the first amplifier anyway? Why can't you just plug survive?
This is even more fun. So the question is, good question. So the question is, why do you need this guy here? Dump him. Just use this guy. Right? Why do you need this guy? You know, big guys rule, right? Who needs the little guys? Well, let me use the Socratic method again. Why don't you give me the answer? You guys are smart. So why do you need little guys? Why do you need the small guy here? Anybody with the answer? Yeah. The big guy may not be as sensitive. I like that. I like that. You know, you know what? He's almost correct. Hey, I'll show you why in a second. Anything else? Any other reason? Any other reason? Yes.
The amplifier is multiplying the signal by a certain amount.
Yes.
The second amplifier is still only multiplying by a certain amount, so if you're trying to multiply by more than that, you're losing the amplifier.
Bingo. That's another good answer. Okay, so let me address both the answers. The answer given was that, look, this amplifier is amplifying the signal by a certain amount, by a factor of 7. Okay, and I've designed this such that this amplifies the signal by a factor of maybe 10. So in all, I'm getting an amplification of 70. Okay, this would be a great design question for lab for next year. You know, I give you a bunch of components and ask you to design an amplifier given the constraints with the highest amount of amplification. It turns out that when you design your amplifier, in order to meet the saturation discipline and so on, you have to choose values of RL and VS and stuff like that, and be within power constraints. Okay? So the amplifier doesn't blow up and stuff. And by the end of it all, you're going to get a measly 7x gain out of it. Same way here, to be able to deal with a very small signal here and get some amplification, another set of values, okay, and you get 10x. Okay, so they multiply. It's much harder to build one amplifier with a much larger gain. And you know what? I just realized, we'll be looking at this in the last 5 or 7 minutes of lecture. I'm going to show you what the amplification depends upon. Depends upon K, depends upon RL, depends upon VI. Okay, now the question is, I've had all this time to think about how to stitch in sensitive into this, and I believe I can. So it turns out that when you have large voltages and so on, and you have practical devices, turns out that the more current you pump through devices, they tend to produce noise of various kinds. Okay, so very powerful amplifiers are not very good at dealing with really tiny signals because they have some inherent noise capabilities. Okay, and so I guess that is sensitive. You know, it's sensitive to noise. So okay, another question? Yes.
So if you need a signal that's the middle size to begin with, why do we need the bump and shrink method if we can just design an amplifier to get the bigger amplification without having to go through the middleman?
Ask me the question again. I didn't follow.
If we have something the size of the middle signal, why do we want to bump and shrink it so we can pass it through a weaker amplifier and then pass it to the big amplifier again, where we can just pass it straight to the big amplifier to begin with?
So I'll just explain. It turns out that I will not be able to pass this to the big amplifier to begin with because this may give me a gain of just a factor of 7. Okay. So, however, if I have a signal that's this big to begin with, then I may just need this amplifier. I don't need the smaller guy. If my signal was this big to begin with, if I had a strong sensor, okay, that produced a strong signal to begin with, yeah, I can deal with just a single stage. I don't need 2 stages. Okay, it's all a matter of design, and it's actually a fun design exercise. You know, given a budget, dollars, right? Given you go to your supply room and look at the parts that you have, and you go to build what you have to build with the parts that you have, right? And so sometimes you need to build 2 amplifiers to get the gain, or build a single amplifier. It's all the design thing. Okay. All right. So moving on to page 7. So that brings us to the small signal model. So page 5. All right. So So what I showed you up on the little demo was that provided the signal input, okay, in this example, VI was much smaller than capital VI, out there as I shrank my input, I was able to get a more or less linear response at the output. Okay? And so to repeat my notation, at the input, the total input is a sum of the operating point input plus the small signal input. Okay, this is called the total variable. This is called the DC bias. It's also called the operating point voltage. And this is called my small signal input. It's also variously called incremental input. Okay, this is more a mathematical term relating to incremental analysis or perturbation analysis. Okay, so VI, you call it small signal, call it small perturbation, call it increment, whatever you want. Similarly, at the output, I have my total variable at the output is a sum of the output operating voltage and the small signal voltage. I don't like using O's in symbols because big O and small O is simply a function of how big you write them. It's not super clear. Okay, and in terms of a graph, let me plot the input and output for you. So let's say this is the total input, and that is the total output. So I may have some bias VI, and corresponding to that, I may have some bias VO. Okay? Hold that thought for a second while I give you a preview of something that we will be covering in about 3 or 4 weeks. Notice that as I couple amplifiers together, the output operating point voltage of this amplifier, okay, in this connection becomes the input operating point voltage of this amplifier, right? So the output, when I connect this output to this input, the output operating point voltage becomes coupled to the input here, so it becomes input operating point voltage here. So now I have a nightmare on my hands. As I adjust the bias of this guy, the bias of this guy changes too. The two are dependent. It's a pain in the neck. And we being engineers find ways to simplify our lives. And you will learn another trick in about 3 or 4 weeks. And that trick will let you decouple these two stages in a way that you can design this stage in isolation. Okay, go have a cup of coffee. Then come back to this stage and design this stage in isolation. Okay? For those of you who want to run ahead and think about how to do it, think about it. Okay, how do you design, what trick can you use to get them in isolation? Okay. Moving on. What I'd like to do next is address this from a mathematical point of view. And much as I did for the light-emitting export dweeb, analyze this mathematically and show you that if VI is much smaller than capital VI, I indeed get a linear response. Okay, so this time around, I won't use Taylor's series. It turns out that this expression can be expanded fully. Okay, so you don't have to buy into Taylor's series and so on. I'm going to list everything down for you. So we know, to begin with, that VO for the amplifier is VS RL K divided by 2 VI minus VT whole squared. Okay, what I'm going to do is, much as I did for the LED, what I'm going to do for this is derive for you the output as a function of the input when the input VI is very small. Okay? In other words, when I substitute for VI, V capital I plus small vi. Okay, much as I did for the export dweeb, I want to substitute for VI a big DC VI. So VI is much smaller than VI. all right, and show you for yourselves that the output response, V small o, is going to be linearly connected to Vi. So notice that, let me write another equation here. This is the total variable. Okay, this simply says that if the input is Vi, then the output is going to be Vo, which means that the operating point input voltage should satisfy this equation, correct? So in other words, the operating point output voltage V capital O should equal Vs minus RL K divided by 2 Vi minus Vt whole squared. This is at Vi equals capital Vi. Okay, this is very simple but may seem confusing. All this is saying is that, look, this equation gives me the relationship between Vi and V0. Therefore, if I apply capital Vi as the input, okay, I'm given that my corresponding output is capital V0, so they must satisfy this equation, right? Those are bias point values, and that must satisfy this equation. Simple. Okay, I know that. So hold that thought. Okay, stash it away in the back of your minds. Okay, now let me go through a bunch of grubby math. And, excuse me, and substitute for Vi this expression here. So let me go ahead and do that. Vs minus RL K 2 when I do something that's other than math, I'll wake you up, okay? So I'll just keep doing a bunch of steps that's pure math, okay? No cheating, no nothing, wash my fingers. When I do anything that's not obvious math, I'll wake you up, okay? So this is, next I'm going to simply move Vt over and rewrite this as follows. RL K by 2 Vi minus Vt plus Vi. Again, I haven't done anything interesting so far. I've just substituted this. I'm just juggling things around, just to while away some time, I guess. All right. Next, what I'm going to do is simply expand this out, right, and write it this way: RL K by 2. Expand that out and treat this as one unit. Squared plus twice plus squared. Okay? Nothing fancy here. So this is like the honest board. Okay? There's nothing fancy here. Standard stuff. Only math. Okay, I'll move to this this blackboard here where I do some fun EE stuff. Okay, yes.
In your middle term, shouldn't you have a small piece of I?
Good, at least one person ain't asleep here. Thank you. Thank you. So just math here, nothing fancy, plain old simple math. Okay, I haven't done no trickery. I still have all my 10 fingers, Okay, now what I'm going to do, now watch me. So I'm not using Taylor's series here because this expression lends itself to this analysis. Notice Vi squared here. I made the assumption that Vi is much smaller than capital Vi. Okay, so what I can do is, assuming that Vt is small enough that Vi minus Vt is still a big number compared to small Vi, what I can do is ignore this in comparison to the capital Vi terms. Okay, so I have a capital Vi term here. Okay, I'm going to ignore Vi squared. So for example, if capital Vi was 5 volts, and small Vi was 100 millivolts, 0.1. Okay, so 0.1 squared is 0.01, so it's comparing 0.01 to 5. So I'm off by a factor of 500, so, so now watch me, okay? It's now I begin, playing some fun and games here. So I eliminate this, and because I eliminate that, it now becomes approximately equal. What I do in addition is let me write down the output. The total variable is sum of the DC bias and the some variation in the output. And let me simply write down, expand that term and write it down again. Minus RL K divided by 2 VI minus VT whole squared. Okay, and I get a minus RL K divided by 2. I get a 2 here, and I get VI minus VT. I won't forget the VI this time. Okay. Again, from here to there, nothing fancy. This is the one step where I've used a trick. I've said VI is much smaller than capital VI, and so I've simply expanded this out and written it here. So do you see the obvious next trick here? So from star, look at this guy. Okay, from star, I can cancel this out from star, because I know that at the operating point, these two expressions are equal, and so therefore I can cancel out the operating point voltage and this. What I'm left with is small v naught is simply RL minus RLK VI minus VT times small VI. Okay, only one place, okay, where I did something funny. Other than that, it's purely math. So this is what I get. So notice that this whole thing is a constant, minus RL K VI VT. This whole thing is a constant, okay? And so V naught is equal to some constant times VI. Let me just define some terms for you that we'll use again and again. For reasons that will be obvious next lecture, okay? I'm going to call this term here GM. So I'm going to call this term K, this is a constant, K VI minus VT. It's a constant for a given bias point voltage, okay? So I'm going to call that GM. And then I'm going to call this whole thing A. And of course, this is VI. There you go. I have my linear amplifier. A is the gain times small VI. And the gain has these terms in it. I just call this GM. You'll see why later. But notice that the gain relates to RL, the size of the load resistor, RL, how big it is, 1K, 10K, whatever. K, this is a MOSFET parameter, and VI minus VT. Okay, that's a constant for a given bias point voltage and small VI. So V naught equals small VI. So I won't give you a graphical interpretation, but I encourage you to go and look at figure 8.9 in the course notes, and it gives you a graphical interpretation of that expression. Okay, move to page 7. So another way of looking at this mathematically analyzing it. So here I went through kind of a full-blown expansion and, pretty much deriving the small signal response. What I can also do is take a shortcut here. So let me just give you the shortcut. You may find this handy. Vs minus K RL divided by 2. And my shortcut is as follows. My small signal response is simply this relationship. Okay, I find the slope of the slope at the point capital VI and multiply by the increment. Okay, slope times the increment gives me the incremental change in V naught as follows. So d by di, Vs minus k RL2 evaluated at Vi equals capital Vi times small vi. Right, this is good old math again. So I want to find out the change in V naught for a small change in Vi, and I do that by taking the first derivative of this with respect to Vi, substituting V capital I, and multiplying by the small change delta Vi or small Vi. So this is simply the slope of the V naught versus Vi curve at Vi. Okay? And so therefore, taking the derivative here of this, this is a constant, so it vanishes. But twice, 2 and 2 cancel out. So I get K RL Vi minus Vt times small Vi evaluated at capital Vi. Okay, so I get twice K RL twice. Vi evaluated at capital Vi, so it's Vi minus Vt times small vi. Same thing. Oh, I have a minus sign here. Okay, I get the same expression that I derived for you out there, and this is just using, taking the slope and going with it. And this, as I mentioned before, this is A. So in the last few minutes, let me kind of pull everything together and also hit upon something that many of your questions touched upon, and that all relates to how to choose the bias point. So here I've taken an analysis approach. Okay, when teaching, we often teach here's something, you're given something, you analyze it. But as you begin to master it, you can begin to design things where you can ask what-if questions and so on. And here, what we have is an analysis given a value of RL, K, Vi, and so on. How to choose the bias point become more of a design issue. Now, if you're designing an amplifier, okay, you ask me the question, how do I choose 2 small amplifiers versus one big amplifier, that sort of stuff. So it boils down to how do you choose the bias point, okay? How do you choose Vi? How do you choose RL? And so on. So what I'd like to do is touch upon some of these things. First of all, gain, or the amplification. One of the most important design parameters for an amplifier is what's the gain. Okay, you go out to, let's say you get a job at Maxim Integrated Technologies, and they say, we'd like you to build a linear power amplifier for cell phones. You can say, I know that. I know how to do that. And then they say, okay, the next stage needs 100 millivolt input, while this thing coming from your antenna is only, a few tens, a few hundreds of a microvolt. So you sit down and say, oh my gosh, I need an amplification of so much. And you go design an amplifier. So gain tends to be a key parameter. And notice that gain is proportional to RL. It relates to Vi minus Vt. Okay, so proportional to Vi. Okay, it's also related to RL. The second point is the gain point determines where I bias something. Okay? If I choose my bias too high, I get distortion. Or if I choose my bias too low, I get distortion. So depending on how I choose my bias point, as the signal goes up, it may begin clipping or may begin distorting. And I'll show you a demo the next time on that particular example. So bias point will determine how big of a signal you can send without getting too much distortion. Okay, and the other thing is that relates to how big of an input what's a valid input range? So let's say you have a signal, and you want that signal to have both positive and negative excursions of the same value, then your input range, depending on where you choose a bias point, your input range may become smaller or larger. And we'll go through these in the context of our amplifier and look at some design issues in the next lecture.